All right, so let's get started on today's awesome lecture. Continuing on what we started last time, which is chapter 3, and there's only like 3 big sections in chapter 3, which is on determinants. So I kind of want to do a little bit of review on what we did last time, and then kind of extend that and talk about some of the applications that we happen to have with this stuff. So let's pick it up where we left off. And last time, and so I started this, and I just kind of want to remind you, there are several different ways to, quote, calculate a determinant. But the key to this is going to be efficiency. What is the most efficient way to calculate a determinant? So again, just to remind you what we talked about last time, if we got the famous 2 by 2 matrix, okay, so if we got a 2 by 2 matrices, you have the A, B, C, D, then your determinant of A is A times D minus B times C. Main diagonal minus off diagonal, okay? However, if you happen to have a 3 by 3 matrix, what you do is, and I just made it general, A11, A12, A13, all the way out to A33 down here. You recopy the first 2 columns, so A11, A21, A31, and then the second column, A12, A22, A32, and then so you copy these guys down, and then you do the same idea. Main diagonal throughout the matrix, so A11 times A22 times A33 plus A21 times A23 times A31 plus A13 times A21 times A33. There's your main diagonal, minus the off diagonal. You work from the bottom and do the diagonals. A31, 8 times A22 times A13 plus, inside the parentheses, but you're subtracting it, A32 times A23 times A11 plus A33 times A21 times A12, and then you're subtracting all that, and that will actually give you the determinant. And we did a problem last time using this particular method, and so just kind of give you some gist on that. So I kind of want to pick up where we left off, and that is another method to do this, because, you know, after about 3 by 3 or 4 by 4, this keep writing the rows and the columns down over again becomes rather tedious and stuff. So there is another method. So picking up where we left off here in section 8.1, if A, and we'll start ourselves out with a 3 by 3 matrices, so definition. If A is a 3 by 3 or bigger square matrix, so n's got to be greater than or equal to 3, then we can use the expansion by minors technique. So this expansion by minors, to calculate the determinant of A, it's equal to, so you're going to pick a particular row or a particular column to do this, and you take, like for example, the first row, you take A11 times what we call the determinant of the minor matrices. So you knock off the row and column in there, and you've got this sub-matrix called A11. And then you got this little, then you alternate signs. Then you do the second element, A12, times the determinant of its minor matrix, plus dot, dot, all the way down. So you get -1 to the n plus 1. A1n, the last element, times the determinant of its minor matrix. And so, again, it's hard to describe in definition terms of what's going on here, but it creates a formula. You want the formula, I'll give it to you. It's the sum as j goes from 1 to n of -1 to the 1 plus j times aij times the determinant of aij. But I can talk about this stuff all day long in terms of the theory. You're going to learn better if I show you an example of expansion by minors. So, here we go. Here is an example. A, something nice, a 3 by 3 matrix. I made this one up. It's 3, 0, 4, 2, 3, 2, 0, 5, -1. Now, right beside this thing, I wanted to do the sign chart for a 3 by 3. You start at the top row, top column element, you know, the first row, first column entry. That's always going to be a plus. And then regardless of the size of the square matrix, they alternate. So if this one starts at a plus, then it's going to be plus, minus, plus. And this one, this is a plus, is going to be minus, plus, minus. Then this one's going to be a plus, minus, plus. They alternate signs. So this is a sign chart for a 3 by 3 matrix, and you're going to need that All right, so pick your particular row or column that you want to expand by. For the example I'm going to do, I'm going to pick the first row. So I'll go ahead and I'll circle that one for you. So the determinant of A is actually equal to, I'm going to pick the first element, and that's a positive term on my sign chart. Pick 3, make them positive, that's the first one. And then you're going to do times the determinant of what we call the minor matrix. That's why this thing's called expansion by minors. You knock off, see where that 3 is at? You knock off the row and column with that 3 in it, and there's a submatrix down here. And so you're going to reduce the size of it. So this was 3 by 3. So if you knock off a row and a column, it's going to make it 2 by 2. And there's your minor matrix, 3, 2, 5, negative 1. So I'm going to write that down here. 3, 2, 5, negative 1. Okay. Now, what's my second entry as I go across? It's a 0, which is great. I love zeros. But I'm going to show you what you're supposed to do. What's the sign of it? Negative. So you're going to do minus that entry 0 times its minor matrix. So where that 0 is at, knock off the row and column with that 0, and you're going to see the minor matrix. It's 2, 2, 0, negative 1. 2, 2, 0, negative 1. And then the next one's going to be a plus as I go across the top. The next sign is going to be a plus. That number is a 4. And then you want to do its minor matrix. So again, to get the minor matrix, you knock off the row and column with that in there, and you can see the minor matrix. This would be 2, 3, 0, 5. 2, 3, 0, 5. Does that make sense? This is the expansion by minors. So I went from a 3 by 3 with the expansion by the minors down to a 2 by 2. We like 2 by 2s because 2 by 2 matrices are real simple to take the determinant of. So the determinant of A is equal to 3 times. Now let's do the determinant of this guy. 3, 2, 5, negative 1. Main diagonal, 3 times negative 1, minus the off diagonal, 2 times 5. Okay, and I'll clean them up in just a second. Minus 0 times 2 times negative 1 minus 2 times 0. Oh, geez, Dr. Taylor, did we actually have to write that one out? No, it's 0 times this. I'm just trying to show you the pattern on these guys. Okay? You like zeros because it completely killed off whatever fellow did. Plus 4 times main diagonal, 2 times 5, minus off diagonal, 3 times 0. And now it becomes arithmetic. So this is equal to, the determinant of A is equal to 3 times, let's see here, 3 times negative 1 is negative 3, minus 2 times 5 is 10, minus 0, okay, fine, times 2 times negative 1, 2 times negative 1 is negative 2, minus 2 times 0, which is 0, okay, plus 4 times 2 times 5 is 10, minus 3 times 0 equals 0. So keep cleaning it up. The determinant of A is minus 3 minus 10, that's minus 13. Minus 13 times 3, oops, sorry about that. Minus 13 times 3 is, so minus 13 times 3 is minus 39. Minus 0, who cares? Plus 4 times 10 is 40. All right. So what is the determinant of A equal to? Negative 39 plus 40? Yeah, 1. There's my answer. It's called expansion by minors. Very helpful technique when you got much larger matrices. And the more important thing is this. You can expand by any row or any column. I did this first example, I just used the first row. I could have used the first column. I could use the second column, a second row, or the second column. Does that make sense? But you have to go with the sign chart. So if I used the second row, it would have been negative 2 times the minor matrices of knocking that guy off the row and column with that in there. And you'll see them, it's 4, 0, 5, negative 1. And you do the same thing throughout. You can use any row or any column, okay? So again, this is kind of important in terms of this. All right, so let me show you another example. Does that make sense? Did I lose you guys anywhere with this? Okay? And again, for larger matrices like 3x3s and 4x4s, instead of keep copying the columns down, this is a little more efficient. Okay? So again, with the terminology here, I'm just going to do another example. The cofactor of a matrix A is the submatrix determinant of Cij, where it's -1 to the I plus j, that's off of your matrix there, times the determinant of that minor matrix Aij. And this is going to give you a numerical value. And so your determinant of A is equal to AI1 times the determinant of that minor matrix Ci1. So the Ci1s are quote unquote the determinant of that minor matrix with the sign this is from the sign chart of the actual matrix itself. Okay, so it's all been put together for you guys in terms of a formula. So it's A12 times AI2 times that determinant of that minor matrix Ci2 with the actual correct sign on it, so forth, all the way out to AIN times the CIN. And these C's are representing what we call the cofactor or minor matrices, okay? Submatrix, if you will, okay? Now, here's what you really want to see. Here's one. It is a 4x4 matrix. It is 6, 0, 0, 5, 1, 7, 2, -5, 2, 0, 0, 0, 8, 3, 1, 8. I want you to find the determinant of this guy. Okay? Again, to be able to find the determinant, I'm going to use what I call expansion by minors. I'm going to draw out the sign chart for this guy, 4x4. Plus, always start on the plus, then alternates, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, and last, minus, plus, minus, plus. It's got to be square, 4x4. Okay? As I mentioned to you before, you can expand by any row or any column. So now here's where strategy and chess games come in at. What row or column would you like to expand by? The third row. Why the third row? Bunch of what? Zeros. Okay, you're looking for the zeros in rows or columns. Okay? So if I was going to do this, my first choice is the third row. My second choice would be the first row, or I could also use the second column, third column, or fourth column, because they all have 2 zeros in it. But the best choice is the third row. Why? Because it's got a bunch of zeros. So, look at your sign chart. This was a plus, minus, plus. So this would be plus 2 times, and now I'm going to draw the minor matrix. So where the 2 is at, knock off the row and column with that in there, and you're going to see your minor matrix of 0, 0, 5, 0, 0, 5, 7, 2, -5, 3, 1, 8. I'm going to write that right here, okay? So 0, 0, 5, 7, 2, -5, and then 3, 1, 8. And then it's going to be minus 0 times its minor matrix, plus 0 times its minor matrix, minus 0 times its minor matrix. Now I wrote that out there for you, but you really don't even care what these guys are, because times 0 completely eliminates it. We picked this particular row for a reason. Does that make sense? But then, leave that 2 right there. Let's focus on the determinant of this matrix. Which row or column would you like to expand by? The first, which one? First row or column? First row. There it is right there. All right? And again, you got to do the sign chart off of it. This will be plus, minus, plus, minus, plus, minus, plus, minus, plus. So it is 2 times, and I'll just put a little bracket right here. It'll be 0 times whatever minor matrix that is, don't care, minus 0 times that minor matrix right there, and then plus, finally got a non-zero term, but it's a plus 5 times its minor matrix. Knock off the row and column, and I got 7, 2, 3, 1. 7, 2, 3, 1. Okay? These terms go away, so I am left with, just cleaning it up, 2 times 5 times the determinant of 7, 2, 3, 1. Well, this one, you finally got it down to something that you like to do, which is your 2 by 2 case. So this becomes 2 times 5 times 7 times 1 is 7 minus 2 times 3. Okay? So this is equal to 2 times 5 times 7 times 1 is 7, 2 times 3 is 6, 7 minus 6 is 1. So what is my answer? 2 times 5 times 1, 10. The determinant of A is equal to 10. Does that make sense? But there is strategy on doing this, so you've got to kind of pick your pigeon in terms of which row or column you want to expand by, and of course you want to do the ones that have the more zeros in it. It really helps you out to get the determinant of these guys, okay? Expansion by minors. Okay, let's do another one. Close I can. All right, this one I'll make up for you. So let's make up one. Again, now I'm trying to kind of put it in terms of how I would put it on the test. Calculate this. 0, -7, 3, 2, 0, 2, 0, 7, 3, -6, 4, -1, 2, -3, and 0, 0, 2. All right, and that's all I put. Calculate the following. Calculate or compute, I can use either word there. What do these little lines around this matrix, these parallel lines around this matrix mean? Determinant. It's a terminology or a notation that when you see without little brackets, the brackets means it's a matrix, but with parallel lines without the little pointies on the end, this means calculate the determinant of this guy. So this sucker is 5 by 5. So now we're getting into really large matrices. So you can sit there and recopy the first 3 columns down if you want to and do the main diagonal minus the off diagonal and be here for a while to do that. Or you can do the expansion by minors. Expansion by minors is going to be a lot more efficient, especially since I got a lot of zeros on this thing. So, question for you. What would you expand by? You got to pick your first row and or column. Second row? No, I'm going to do second column, just to mess you up. Okay, second column. This one. I know, I could have done the other one, but we just did a row. I want to do a column now, just to let you know that I can do something different than a row. It doesn't matter. I mean, you're going to get just beauty math. There's only one answer. More than one way to get there. I'm going to do the second column because most people don't see that one. All right, but you got to do your sign chart here. And in terms of the sign chart, this one is positive, right? So what's your next one going to be? negative, then it'll be plus here, minus, plus, minus. And I don't need to do the entire chart, I just need to know the same positioning. Does that make sense? So, it's minus, plus, what about that 3 right there? What sign is that one going to be? Negative. So that's why I want to do this one. So the determinant, let's give this guy a name, let's call him A here. The determinant of that matrix A is equal to negative, because of the sign right there, 3 times, what would the minor matrix be? Knock off, I don't care about the rest of them because they're a bunch of zeros, so I'm not going to write the zeros. Knock off the row and column with this thing, okay? And you have to kind of visualize this. If you knock off the row and that column right there, you end up getting 4, negative 7, 3, negative 5. Make sure I don't screw this up. 4, negative 7, 3, negative 5, okay? Knock off the row and column with this guy. Okay. Knock off that row. Let's see here with that column. And what am I left with? 0, 2, 0, 0. Agreed? Row and column over here. 5, 5, 2, negative 3. 5, 5, 2, negative 3. And then the last row would be 0, 9, negative 1, 2. Did I lose you guys anywhere in terms of my submatrix when I knock the row and the column out with this guy? So get my pen that likes to roll around on me. Okay, the row and the column that we're knocking out here, where the 3 is at, and then you can actually see literally the rest of the measure minor matrix and where I've got this guy from. Okay. Does that make sense? All right. Now, knocked it down from a 5 by 5. Now I'm down to a 4 by 4. Which one you want to expand by now? Because you basically start the game all over again. I would do, okay, now I'm going to go for that second row. But again, I got to do my sign chart. This is going to be plus, so your next row will be a minus, plus, minus, plus. Does that make sense? So this is going to be a negative, a 3 times, and I'm going to pick 0, this is negative, this will be a plus. That'll be a positive 2, okay, times, and knock off the row and column with that guy in there. Knock off the row and column, and I get 4, 3, negative 5. Okay. 5, 2, negative 3. Knock off the row and column with that guy in there. And I got 0, negative 1, 2. Did I lose you guys anywhere on that one? Yeah. Which one? This one right here? That's a plus. And you know where I got the plus from? You see that 2 right there? That I just recopied that sign. That's an actual little plus that I put there. Okay. That minus came from this particular position when I chose him there. So there you go. So your signs have to go with it. So now I got a 3 by 3. How do you want to find it? Question? Yes, ma'am. Uh-huh. Yeah, I could do one. I did the first one. I'd use the first row, and then I look at the minor matrix, and then I really like that second. First I did the second column. Then I really like that second row because it had a bunch of zeros in it. This one right here, well, I can let you know right now with this one, I'm either going to pick the first column or the first row. That's your choice, only because at least one of them's a 0. I'm losing my zeros. It's my problem here. So I'm going to go after. Let's go back to columns because that's a little different for you guys. Okay, I'm going to expand by that one. Again, for the 3 by 3, it's going to be a plus, minus, plus, right? On the 3 by 3. So this is equal to that negative with the 3 times that plus 2 times, here we go, I'm going to expand by bracket right here. Here we go. I'm going to use this column. That is 4. That's going to be a positive 4 times the minor matrix. Knock off the row and column with that in there. And I got 2, negative 3, negative 1, 2. Okay. And now it's going to be a minus on the 5 times, you knock off the row and column with that guy on there. I got 3, negative 5. And the negative 1, 2. And then it's going to be back to plus. Then this guy is going to be 0 times, and this is just practice on the minor matrix down there, minors. The 3, negative 5, 2, negative 3. 3, negative 5, 2, negative 3. Does that make sense? I mean, it's just tedious. And you, again, I warned you guys from day one in this class. What is the thing that will kill a grade faster than anything in this particular class? Careless error. Bonehead, basic 2 times 2 is 22 arithmetic, you know, that kind of crap. Be careful. So, who cares about time 0, right? I just wrote that for your benefit there. So here we go. This is equal to negative 3 times 2 times 4 times 2 times 2 is 4 minus negative 3 times negative 1 is a positive 3. Minus 5 times 3 times 2 is 6 minus negative 5 times 1 is 5 plus 0 there, okay? So this is negative 3 times 2 times 4 times 3 times 4 minus 3 is 1 minus 5 times 6 minus 5 is 1. So this gives me negative 3 times 2 times 4 times 1 is 4, 5 times 1 is 5, 4 minus 5 is negative 1. So what's my determinant? Negative 3 times 2 times negative 1 is what? 6. The determinant of A, or this calculation here, is actually 6. Does that make sense? But it was strategy. If I picked the wrong row or the wrong column, I could be here for a little bit longer. It's just arithmetic, but I am going for the 0 rows or the 0 columns on this stuff, okay? And what's important, also equally important in the terms of your setup, is the actual sign charts you have to set it up with. Does that make sense? All right. Keep it going. How bad can it get? Oh, wait. Okay, we can always try to make it worse. All right. Section 3.2, the property of determinants, or properties of determinants, if you will. Okay? All right. So, you get a feel for where we're going with this by the big theorem, Theorem 3 out of your textbook here. It says, the property of determinants. Row operations. Let A be an n by n, I had to be square matrix here, n by n. Number 1, if we multiply, if a multiple of one row of A is added to another row of A to perform matrix B, then the determinant of B is actually equal to the determinant of A. So if I'm doing the old classic row echelon form stuff, manipulating my matrices because I'm trying to throw some zeros in there, why would I want to do that? Did you not pay attention to all the stuff we were just doing on the expansion by minors? What were we always looking for? Those rows of zeros and columns of zeros and stuff like that. So I like to have zeros in there. What if you don't have zeros in there? Well, let's make some. How do I make some? Row echelon form. What's the first thing? I multiply one row by a constant, add it to another row. Whatever row I add to is the row I replace. Row echelon form. If that happens and you get this new matrix that has that 0 thingy that we're after in it, the determinant of the new matrix is equal to the determinant of the old matrix. It doesn't change the determinant. That's helpful. 2. If 2 rows of A are switched to perform B, then the determinant of that new matrix B is equal to negative the determinant of A. Now, this is the way the textbook wrote it up. The new matrix determinant of B is equal to negative determinant of A. The reality is, look, I'm giving you a crappy matrix, and I want you to find the determinant of it. So I'm still looking for the determinant of A. So I wrote it over here, and what I'm basically circling is the ones you're actually going to use in terms of your notation. The determinant A, the original matrix, will actually be equal to negative determinant of that new matrix B. Now, I think you can see the negative. It doesn't matter which side of the negative you put it on. If you switch two rows, it makes a negative on this thing. And then, wait, there's property number 3 here on theorem 3. If one row of A is multiplied by a constant to form matrix B, then the determinant of matrix B will be equal to that constant K times that original determinant of matrix A. So this is a way of thinking about it here, okay? If you multiply K times a particular row, because I need to make it a pivot, so I want to multiply it times 5, because I had a 1/5, because I had a crappy fraction on this thing, okay? The determinant of that new matrix B is equal to 5 times the determinant of the old matrix. But that's not really helpful, because what I'm going to ask you guys to do is find what's the determinant of the original matrix A. Not of the new matrix, but the old matrix. So what happens? Move the K to the other side. So the determinant of A is equal to 1 over K times the determinant of that new matrix. That 1 over what you multiply by times the determinant of the new matrix. That's going to be when most people are going to fumble the ball in here. It's 1 over the constant you are multiplying by. Okay? So there are 3 moves we're going to make. Now this comes from your row operations. What were my original row operations? Swap 2 rows. 1. Multiply a row by a constant. 2. Multiply 1 row by a constant, add it to another row, and whatever you add to, you replace. That was your big move on reduced row echelon form stuff. Those are the 3 moves, and I'm showing you how it affects the determinant of that original matrix. That's what these circle blocks are all about. This is what you're going to need, okay? So, here's my old crappy handwriting on this one, but here it is. What's the big idea with this stuff? The big idea is this. Using the definition of the determinant of A is inefficient for large matrices. If I give you 17 by 17 matrix, go find the determinant of that guy, you're going to cry, okay? Because it's awful. I mean, and also I took the batteries out of your calculator, so it's worse than you know. All right, so, and you got to do this thing, and your life depends on it. So it's real important you get it right. So, what am I going to do? We'll go back to our old rules. So, to make it more efficient here is this strategy. Reduce A to echelon form to find the determinant of the matrix A. Now, notice one thing in my crappy handwriting here, the strategy here. Reduce A to echelon form. I did not say reduced row echelon form. You're just wasting your time and spinning it. Now, that's a great way to solve the equation, but I don't want to solve it. I just want the determinant of it. So what is echelon form? Pivot, and it doesn't have to be a 1, right? Just a pivot spot, and zero's where? Just below it. I want this thing to be what we call upper triangular. Pivots, not necessarily 1 pivots, just pivot positions, and zeros below it. That's row echelon form. Reduced row echelon form is make a pivot of 1 and zeros above and below all the pivots. That's reduced row echelon form. All we're going after is row echelon form. And the reason for that is this. Big note. The determinant of an upper or lower triangular, remember, it's square matrix, is the product of the diagonal entries. You need this in your notes. If I've got a matrix that is either upper triangular or lower triangular, and it's square so we can find the determinant of it, all I got to do is multiply the entries of the main diagonal, and that'll be what the determinant is. So, let me give you an example of that one here, okay? I'm just gonna make up one for you right here, here we go, something free, note. What is the determinant of 3, 5, 7, negative 45, 0, 2, 6, 0, 0, 0, negative 5, 402, okay? 0, 0, 0, negative 10. Okay? Compute. Just trying to show the different words I throw at you for these kind of directions. This is free points. Again, you can do the expansion by minors. Okay, let's do expansion by minors in our head. What row or column would you expand by? Column 1. So it's going to be 3 times this minor matrix. Now, what row or column are you going to expand by on this minor matrix? Second, I'll go for the second column there. I mean, excuse me, the first column there, right? So it's going to be 2 times. Okay, what's the term of the 2 by 2? It's the main diagonal minus the off diagonal, but the off diagonal has the 0 in it, so it's going to be 0. What's the end result? You just multiplying the diagonals of your matrices. That's the essence of either being upper or lower triangular. So the answer is very simple. What is the determinant of the matrix 3, 5, 7, negative 45, 0, 2, 6, 0, 0, 0, negative 5, 402, 0, 0, 0, negative 10? It is 3 times 2 times negative 5 times negative 10. That's what? 6 times 50. I think I can do that. What is that? 300? That is my answer. You love a triangular, upper triangular or lower triangular, doesn't matter. But a triangular matrices, all that is when you do the determinant, it's the product of the main diagonal. Does that make sense? Questions? All right. So that's what I'm referring to with this. Finding the determinant of an upper or lower triangular is the product of the diagonal entries. And you get that from the expansion by minors, and you pick the right guy that has all the zeros in it, and those zeros keep helping you out with that upper triangular with all the lower parts being zeros. Okay? So let's do this one. Find the determinant of A if A is equal to 1, 3, 3, negative 4, 0, 1, 2, negative 5, 2, 5, 4, negative 3, negative 3, negative 7, negative 5, 2. And I read this stuff to you guys in case you can't read my handwriting, but hopefully you can read. Yeah, I'm really going out of my way to put the little minuses on there so you can see them. Okay? All right, so here we go. If I was going to do expansion by minors, I would either expand by the second row or the first column. You with me? Because it sucks. I only got 1 0 in this whole 4 by 4 matrix. I only got 1 0. Okay, I can do it, but there's a better way. Because I don't have that many zeros, or 1, maybe sometimes you get none, what I'm going to do is I'm going to do the I'm going to go for row echelon form. Go back to my old standby. So what would your first move be if you were going to do a row echelon form? All right, so echelon form. I was nice enough to go ahead and make that sucker a pivot for you, right? Okay, Merry Christmas. Sweep down. Already got a 0 there, so I don't have to do anything. So what's my next move? I'm going to do what? Negative 2 times row 1. I'm going to add it to row 3. And whatever I add to, I replace. And then I'm going to sweep down and multiply 3 times row 1, add it to row 4, replacing row 4. Does that make sense? What does that give me? Let me make sure I don't screw this up. Okay, so 1, 3, 3, negative 4. That zero is already there. 0, 1, 2, negative 5. Okay? Now, negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times 3 is negative 6 plus 5 is negative 1. Negative 2 times 3 is negative 6 plus 4 is negative 2. Negative 2 times negative 4 is positive 8 plus negative 3. 8 minus 3 is 5. Agreed? Okay, keep going. 3 times 1 is 3 plus negative 3 is 0. 3 times 3 is 9 plus negative 7 is 2. 3 times 3 is 9 minus 5 plus negative 5 is 4. And 3 times negative 4 is negative 12 plus 2 is negative 10. Agreed. Question for you. What is the difference? What is the difference between the determinant of A and the determinant of this new matrix right here? According to our theorem, I multiplied one of the rows by a constant and added it to another row and replaced that row. According to our theorem, what is the difference in the determinant? What's the calculational difference between the determinant? Not K, no sir. Here, number 1. If a multiple of one row of A is added to another row of A to form matrix B, then the determinant of the new matrix B is what? Equal to the determinant of A. So what I'm telling you right here is the determinant of this guy and the determinant of this guy are what? The same. They're equal. Multiplying a constant times one row, adding it to another row, and replacing that row with it doesn't change the determinant. Does that make sense? That is theorem 3, number 1 at its best. You don't have to do anything. So the determinant of A and the determinant of this new matrix B here is the determinant of A equals the determinant of B. So I don't have to worry about manipulating a constant to it. Does that make sense? They're the same thing. All right? What's your next move? Well, I got this new pivot right here, 1, and Merry Christmas, it's a 1. Now I'm going to sweep down and make some more zeros. I'm going for this upper triangular thing. That's what I want to do. I'm going to go for echelon form. So I'm going to take row 2, and just add it to row 3 and replace row 3. I'm multiplying 1 times row 2, adding it row 3, so it follows from my theorem. And then I'm going to multiply negative 2 times row 2, add it to row 4, and replace row 4. So I'm going to call this C matrix here, okay? I'm going to get 1, 3, 3, negative 4, 0, 1, 2, negative 5. Here we go. 0 plus 0 is 0. 1 plus negative 1 is 0. 2 plus negative 2 is 0. Negative 5 plus 5 is 0. Okay? That's kind of nice. All right, now keep going here. And now I'm going to sweep down just to finish my job. Negative 2 times 0 is 0 plus 0 is 0. Negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times 2 is negative 4 plus 4 is 0. Negative 2 times negative 5 is 10 plus negative 10 is 0. Okay, I got a question for you. What is the difference between the determinant of B and the determinant of C? None. Multiplying a row by a constant, adding it to another row, and replacing it doesn't change the determinant. So here, the determinant of A is the same as the determinant of B, which is now the same as the determinant of C. What's the determinant of C equal to? You got it now to be upper triangular. And it just so happens I got a 0 on the diagonal, which makes it nice. So this will officially be 1 times 1 times 0 times 0, which is 0. And since they're all equal to each other, the original determinant of that matrix A that we started with is 0. That's kind of nice, but there you go. Did I lose you guys anywhere? Well, geez, this was the easy one. That's right. I chose the easy one to immerse you into this stuff. So, let us keep it going, okay? Let's compute this dude, okay? He's a little more challenging, okay? I have the matrix 2, -8, 6, 8, 3, -9, 5, 10, -3, 0, 1, -2, 1, -4, 0, 6. Okay? I want you to calculate the determinant of this guy. Okay? Again, you know when I look at this matrix and I'm supposed to calculate, and it's a big matrix, 4 by 4, I won't give you anything bigger than 4 by 4s or 5 by 5s. I mean, after a while, it's just beating a dead horse. I understand the concept here, but I want it big enough that, that one of these other methods are not more efficient, like, a 2 by 2 and a 3 by 3. You can get some of those things quickly, even by expansion by minors, maybe faster than me trying to do the row echelon form stuff here. This one's big enough that you can see the efficiency of the reduced row echelon, or the echelon form of this stuff is what I'm after. So, a couple of things I could do on this guy right here, but I want to calculate the determinant of it. First thing I notice is this. I don't have hardly any 0 rows or 0 columns. Now, I got 1 0, maybe a couple of zeros down here. That's great, but 1 0 at a 4 by 4 is not that helpful. Does that make sense? So, I'm going to go for my echelon form thing here. But, my first move. Now, there's a couple of things you can do here if you wanted to. Well, you could do a row swap on this one. You could do that. And then what's that going to do for you? Well, let me pull out this while I left my little paper up here so you guys can see it. If I do happen to do a row swap, how is that going to affect my original determinant, which is what I'm after? If I determine this guy, it will be negative the determinant of the new matrix. I could do it that way. However, I'm going to make it even a little more challenging for you. I happen to notice that top row, because I really want that pivot right there. They're all even integers, right? So what I'm going to do here is this. I am going to multiply 1/2 times row 1. That's just as efficient to get that pivot right in that first spot. Does that make sense? And if I do that, what is that going to give me? 1, -4, 3, 4. The rest of the matrix is the same. 3, -9, 5, 10, -3, 0, 1, -2, 1, -4, 0, 6. And remember, these little absolute value lines mean the determinant of. But that right there affects my determinant. Now, how does it affect it? Again, back to my theorem up here, theorem 3. Okay, when you multiply a row by a particular constant, how does it affect the determinant? Well, the book says this. If, this is part 3, if one row A is multiplied by a constant k to get matrix B, then matrix B is equal to k times the determinant of A. We don't care what the determinant of B is. We want to know what the determinant of A is, the original matrix. This is the way they wrote it in the book, but I'm writing it for you this way, so because we're always after the determinant of the original matrix. The determinant of the original matrix is going to be 1/k times the determinant of the new matrix. This is the new matrix, right? So, what am I going to have to get out here to actually make sure that the determinants are actually equal to each other? Outstanding. It is 2. I want to write it this way. It's 1/k, and your k value is 1/2. Does that make sense? It's that 1/k, 1/2 makes it a 2. That's what the effect is. It's going to be 2 times 1/that half that we multiply by times the determinant of this new matrix. Now, what's my next move? sweep down. So it'll be basically -3 times row 1 added to row 2, replace row 2. It'll be +3 times row 1 added to row 3, replace row 3. And then it'll be -1 times row 1 added to row 4, replace row 4 to get those zeros in there. Keep that 2 out front, because remember, this is not just a matrix, it's a determinant. So it's 2 times, this will be 1, -4, 3, 4. Let's sweep down. -3 times 1 is -3 plus 3 is 0. -3 times -4 is 12. Plus, -9, 12 minus 9 is what? 3. -3 times 3 is -9 plus 5. -9 plus 5 is -4. -3 times 4 is -12 plus 10 is -2. Agreed? And you know right here is where people fumble the ball is they can't do the arithmetic in their head. So sometimes I need to slow down and double check myself. But okay, I feel good about this one because I have the answer over here. So yes, I did the math correct. Just take your time. Now, 3 times row 1 added to row 3. 3 times 1 is 3 plus -3 is 0. 3 times -4 is -12 plus 0 is -12. Okay? And double check myself on this one. So, yes, -3, double check myself, 3. 3 times -4 is -12 plus 0 is -12, okay? 3 times 3 is 9 plus 1 is how much? 10. 3 times 4 is 12 plus -2 is 10, all right? Now, -1 times row 1 plus row 2. -1 times 1 is -1 plus 1 is 0. -1 times 4 is -4 plus 4 is 0. -1 times 3 is -3 plus 0 is -3. And -1 times 4 is -4 plus 6 is 2. Okay? What effect does that have on my determinant? Multiplying row by a constant, adding it to another row, what effect does it have? The same. No manipulation. Does that make sense? Let's keep going. What's your next move? I'm going to sweep down. Don't make him a pivot. I mean, I could, but there's no reason. I can make him a 0 by taking this and sweeping him down. I'm not going for reduced echelon form, so I don't have to make my pivots 1. All I want to do is make zeros below it. So 3's go, great. I can just multiply it times 4 and add it to the -12, right? So that's what I'm going to do. So here we go. It'll be 4 times row 2, add it to row 3, replace row 3. Again, that 2 is still out front, so I got 1, -4, 3, 4, 0, 3, -4, -2, and here we go. 4 times 0 is 0 plus 0 is still a 0. 4 times 3 is 12 plus -12 is a 0. 4 times -4 is -16 plus 10 is what? -6. 4 times -2 is -8 plus 10 is 2. And then let's copy down the last row here. 0, 0, -3, 2. Did I lose you guys anywhere? What's your next move? Let me know what your next move is. Well, yes, okay, fine, but I want to go for that diagonal thing. So I want one more, because I'm really trying to use the echelon form on this thing. This is not an echelon form. I want echelon form. What would you do? Very good. You want to make this guy a pivot, but your goal is to get this guy down here, right? So I would do this. Multiply -1/2 times row 3 and basically replace row 3 with that. Does that make sense? You could, but what if you row swap, what are you gonna do? Make it a negative. You could have done that too. I'm just trying to do this constant thing because that's where most people are gonna screw it up at. So there's method to my madness, but you're right. You could have row swap it and that would have been, but you would have to throw a -1 in on that. So there is a manipulation here. So this would be 2 times, a little space there. This would be 1, -4, 3, 4, 0, 3, -4, -2, 0, 0. We're going to multiply -1/2 here. -1/2 times -6 is what? 3. -1/2 times a negative times a +2 is a -1. And then we got 0, 0, -3, 2. Question for you. How does the determinant of this guy manipulate to get the determinant of this guy? What's the deal? What was your constant K in now? -1/2. And how does it affect it? Again, when you multiply a row by a particular constant to retain matrix B, the original matrix, that new matrix B will be equal to K times the old determinant of A. But again, we're after the determinant of A. So the determinant of A will be 1 over K times the determinant of this new matrix. This is your new matrix. So what you got? Yeah. But I'm just trying to do it in a different way because I'm trying to show you constants. So there's lots of different things I could do to this thing. I could multiply -1/2 times row 2 and add it to row 3. That would make the -6 and 2 still stay there though. But then it would not change my determinant at all. But this one does. And what is it to change it by? Well, it's going to be that 1 over, now your K is -1/2. So what does that make it? -2. Does that make sense? This is that 1 over K thing from this maneuver right here. This is why I put this in your notes versus what's in the textbook. All right. Now, one more move. What's your next move? Sweep down. How about row 3, add it to row 4, replace row 4. This will give you 2 times -2 times 1, -4, 3, 4, 0, 3, -4, -2, 0, 0, 3, -1. Now, sweep down. Just add them together. 0 plus 0 is 0. 0 plus 0 is 0. 3 plus -3 is 0. -1 plus 2 is 1. Agreed? This was my ultimate goal. This is what I'm after. If I have to keep up with how it affects the matrices with these numbers out in front and stuff, and if I swap 2 rows, that's a negative. I didn't do that on this one. So what is my actual answer? So the determinant of A, which is that original matrix up here, and this just, I wanted to clarify, this is the A matrix here. The determinant of A would be equal to 2 times -2 times what? 1 times 3 times 3 times 1, the main diagonal. Does that make sense? So let's do some math here. 2 times -2 is -4. 1 times 3 times 3 times 1, what is that, 9? Times 9, what is the answer? -36. And that is my determinant. Did I lose you guys anywhere with this thing? And how it affects it, stuff like that. And so, I've shown you guys how many ways to take a determinant. Well, it depends on the size, but 2 by 2 is kind of your special case of main diagonal minus off diagonal. But the rest of them, you can reduplicate the columns and main diagonal going down minus the off diagonal going up. You could also do the expansion by minors technique. You can also do echelon form, but you have to keep up with the thing. So there's 3 different methods. And why we teach you guys 3 different methods is it really depends on the size of the matrix, which one's going to be the most efficient in being able to get the determinant. Once you get to a certain size, usually it's around 4, okay? 4 or bigger, doing the echelon form on this thing and getting it just to be upper triangular and keeping up with how it affects the determinant is going to be the most efficient way to actually get the determinant of the matrix. Does that make sense? But if it's 2 by 2, you don't need this mess. It's main diagonal minus off diagonal. If it's 3 by 3, expansion by minors is a pretty good way to do this thing. You know, and look for those row of zeros. If you don't have row of zeros, you'll quickly get it into 2 by 2 matrices that you can manipulate. Again, efficiency is the key to this stuff. Does that make sense? Have I lost you anywhere? All right, keep on going then. So, some more about these determinants and the like here. And that is this. All right, a couple of things we want to talk about. Again, another reason why we want to know about this determinant thing. Remember, that means I've actually mentioned this mess to you before. Remember, the determinant of A is not equal to 0, then A is a non-singular. And what does non-singular mean? Which means A is invertible. So one of the reasons we want to know about the determinant of A is whether it is going to be invertible or not. Does that make sense? So we're after that, okay? If the determinant of A does equal 0, then we call A singular matrix. Singular means non-invertible. A singular matrix is a non-invertible matrix. It's a fancy terms here, okay? So the determinant really does allow us to figure out immediately if it's going to be invertible or not. The next thing is this. What is the difference between A and A transpose? Now, A transpose, you just switch the rows and columns around. You know, rows become columns and columns become rows. But in terms of the determinants, the determinant of A and the determinant of A transpose is exactly the same thing. It doesn't matter if the row becomes a column or the column becomes a row on how you manipulate a determinant. You're going to still get the same answer. Okay? Now, some more theorems about this. One major theorem, it's a formula, is this. If A and B are n by n, square matrices, this only works with square matrices because you've got to take a determinant. You can only take a determinant of square matrices. Then, the determinant of A times B is equal to the determinant of A times the determinant of B. This is a property of determinants. So, if you can somehow, got two matrices, A and B, and you take the product of those things, if you want to figure out the determinant of that A times B, all you do is figure out what the determinant of A was and what the determinant of B was, and the product of that would be the determinant of A times B. The only way I can actually show you this is do an example. So if I'm going to do an example just on this property, I'm going to do a 2 by 2 because it's the easiest thing to take a determinant of. So here's two matrices, A and B. A is 4, -3, 1, -2. Okay? And B is 0, -3, -2, 10. What is the determinant of A? The determinant of A is going to be 4 times -2 minus -3 times 1. 4 times that -2 is -8 minus -3. Minus and minus makes it plus. I believe I get -5 on that. Agreed? What is the determinant of B? The determinant of B would be 0 times 10 minus -3 times -2. Main diagonal minus off diagonal. 0 times 10 is 0, minus -3 times -2 is 6. 0 minus 6 is -6. What's the determinant of A times B? Well, it better be 30. Let's take a look, all right? What is A times B? Row by column. It's 4 times 0 plus -3 times -2. -3 times -2 is 6. 0 plus 6 is 6. Does that make sense? First row, second column. 4 times -3 is -12. plus negative 3 times 10, which is negative 30. Negative 12 plus negative 30. Negative 12 minus 30 is what? Negative 42? Agreed? Second row, first column. 1 times 0 is 0. Negative 2 times negative 2 is positive 4. 0 plus 4 is 4. And then last row, last column here. 1 times negative 3 is negative 3. Negative 2 times 10 is negative 20. Minus 3 minus 20 is minus 23. That's what A times B is, right? What is the determinant of A times B? It's going to be 6 times negative 23, mang diagonal, minus off diagonal, 4 times negative 42. All right, time for a calculator now. So if I figure out what I did with my calculator. All right, so 6 times a negative 23 is a negative 138. Negative 4 times a negative 42, negative times a negative is a positive. 4 times 42 is plus 168. Feel better about my math. What is negative 138 plus 168? 30. Okay. So I get 30, which just so happens to be the same thing as the determinant of A times the determinant of B. Negative 5 times negative 6. Always works out that way, but there you go. Does that make sense? However, a special note on this guy is this. This works with products. The determinant of A times B equals the determinant of A times the determinant of B. It doesn't work with addition or subtraction. The determinant of A plus B does not equal the determinant of A plus the determinant of B. It doesn't work like that. You can sit there and add these two matrices together, and you'll end up getting what? You can sit there and very easily figure out that these two determinants are not going to be equal to each other. Okay? It does work with the multiplication stuff. Questions? All right. Section 3.3. Section 3.3 is, again, more applications of these determinants. What can you do with these determinants? Now, we're going to do lots of things, and again, I'm going to reach out for my Calculus 3, but I know a lot of you guys haven't had Calculus 3 yet, but don't worry, I'm going to show you some stuff, but only in this context here. But there's something called Cramer's rule that we use determinants for. And we also can do volume and linear transformations, volume and area, and then we can also manipulate the linear transformation stuff here. All right. Cramer came up with this wonderful use of determinants, which is just fascinating. And again, for you computer science majors, it is rather interesting that you'd be able to program. Cramer's rule says this. If you got an equation, matrix equation, AX equals B, okay? You got your matrix A, which is your coefficient matrix of your variables, X, X1, X2, X3, whatever you got there, equals the vector B, where A is going to be n by n, it's going to be square. And we're going to define, this is a notation, AI of B. This AI of B is going to be a new matrix. And again, it's columns. So you've got this AI, so you've got the A matrix. But on the ith column, you're going to replace the ith term with the B vector. The ith column vector with the B vector. So you get A1, A2, A3, AI minus 1. Right where AI is, you put in the B vector, and then you're back to AI plus 1 all the way up to AN. This is the ith column. Replace it with AI with the B vector. Okay? The rule is this. Let A be an n by n invertible matrix. Then for any B in Rn, wherever you set it equal to, the unique solution of x of the equation AX equals B can be found by the x variable, with xi, we have x1, x2, x3, what it is. Xi is equal to the determinant of that AIB, which is what we were talking about up here, the determinant of this matrix, divided by the determinant of the original matrix A, and for I equals 1, 2, 3, all the way up to the end. Okay? Now, again, for my computer science majors out here, we are talking about efficiency for this. You know, there's lots of different ways you can solve matrices and stuff, matrix equations. This is one way, and again, we're talking about efficiencies here. So, first off, number one, A had to be invertible. Why? Well, what is the determinant of a non-invertible matrix? What's the determinant of a singular matrix? 0. And look at my formula. I can't divide by 0. I don't get answers that way. So you've got to make sure determinant of A is non-zero, which means it's non-singular, which means it is invertible. Okay? And also, Cramer's rule is only efficient, aka we only really use this stuff up to 3 by 3. 3 by 3 matrices, or 3 equations, 3 unknowns. After that, it doesn't become efficient. Because don't forget, you got AX equals B, you could find A inverse, multiply by A inverse on both sides. You could sit there and do the reduced root echelon form of these guys and get X1 equals 5, X2, you can figure out the answers that way. There's a lot more efficient ways. But Cramer's rule was interesting because, one, how long ago it came up, and the wonderful use of using determinants with the matrix. So, I got 3 minutes left. Perfect time to do one example. So, understand, when I just told you, because of my efficiency being up to 3 by 3, bank on a Cramer's rule is either going to be a 2 by 2 matrix or a 3 by 3 matrix. That's pretty much what you're going to get. So here we go. I want you to use Cramer's rule to solve this system. 4x1 plus x2 equals 6. 5x1 plus 2x2 equals 7. The first thing you should do with a system of equations is write it as a matrix equation. So this would be the matrix 4, 1, 5, 2. That's my coefficient matrix. That's matrix A. Times the x matrix, x1, x2. We'll call him just the x vector, if you will, is equal to, the b vector would be what it's equal to, 6, 7. Does that make sense? All right. Here is the deal. There's 2 things you want to solve for, x1 and x2. x1, you divide by the determinant of the A matrix, which is the 4, 1, 5, 2. Now, what you do for x1, you take the first position of A and replace the first column with the B column, 6, 7. So this becomes 6, 7, 1, 2. Does that make sense? I replace that first column is B, the 6, 7, but the rest of matrix A stays the same. And for x2, you divide by the matrix, the determinant of matrix A, which is 4, 1, 5, 2. But here, it's x2. So you're going to replace the second column with B. Back to your A matrix, it's 4, 5. But the second column, you replace it with the B, which is your 6, 7. So notice the positioning of the 6, 7. For x1, it's in the first column. For x2, it's in the second column, but you divide by the original matrix A. Now, let's go find what the answer is. It's 2 by 2, so here we go. It'll be 6 times 2 minus 1 times 7 divided by 4 times 2 minus 1 times 5. So that's 12 minus 7 divided by 8 minus 5. 12 minus 7 is what? 5? 8 minus 5 is 3. So pretty much x1 is going to be 5/3. Now what about x2? 4 times 7 minus 6 times 5 divided by 4 times 2 minus 5 times 1. 4 times 7 is 28 minus 6 times 5 is what? 30 divided by 4 times 2 is 8 minus 5 times 1 is 5. You should always get the same denominator, which is 3. 28 minus 30 is how much? -2. So that tells me x2 is equal to -2/3. And so the x vector that solves this system of equations is 5/3, -2/3. And it's very efficient. If I was trying to do row echelon form or whatever, I'm still trying to get bits and pivots and that thing and stuff like that. We'll work on some more on these things up, but here's a great and wonderful way of using the determinant to be able to solve a system of equations. So this determinant is interesting where it's used at in matrices. Study hard, and I'll see you guys on Thursday.